First of all, thank you very much to all of our fellows and distinguished awards that will be here present in this magnificent building, and we are hosted by the President of the Royal Academy of Spain. But before going ahead, I would like to say that during the break, Professor Pombeiro will make an exposition about where will be the next symposium that will be also in a very beautiful place, which is in the Academy of Lisbon, which is also a very old building, a very, very matured one. Saying so, and expecting the best for all of you, is let me try to introduce the Leonardo da Vinci Prize. Is the most prestigious prize that our Academy supports. Is really a prize that for the recognition of the great contributions that researchers give in the field of science as a whole. And this year is with, I am the pleasure and honor to distinguish, and all of us, we distinguish by unanimous vote, to attribute this prestigious award to Professor Reddy. He is a distinguished professor and Regents Professor and inaugural holder of the Oscar of S. Wyatt Endowed Chair in Mechanical Engineering at Texas A&M University College Station in Texas. Professor Reddy has been a prolific researcher and passionate teacher, and he served the profession admirably. Dr. Reddy, as a highly cited researcher, is known for his significant contributions to the field of applied and computational mechanics through the authorship of nearly 700 journal papers and 21 textbooks. Professor Reddy received his Bachelor of Engineering degree from Osmania University, Hyderabad, India in 1968, and Master of Science degree for Oklahoma State University in Stillwater, Oklahoma in 1970. He obtained his PhD in 1974 in engineering mechanics from University of Alabama in Huntsville. He worked for a short period for Lockheed Missiles and Space Company in Huntsville, Alabama, before joining the University of Oklahoma as an assistant professor in 1975. He was promoted to the rank of associate professor in 1978, and in 1980, he was recruited as a full professor in the Department of Engineering, Science, and Mechanics at Virginia Polytechnic Institute and State University. In 1986, he was named the inaugural holder of the Clifton Garvin Professorship in Engineering, Science, and Mechanics Department. In 1992, he was recruited in a nationwide search as an inaugural holder of the Oscar Wyatt Endowed Chair in the Department of Mechanical Engineers at Texas A&M University College Station. In 1998, he was appointed as the University Distinguished Professor. Only top 2% of the distinguished professors, they occupy this position, and moreover, he got a lot of positions worldwide since then that I will just will not cite all of them. His pioneering work on the development of shear deformation theories that bear his name in the literature as the Reddy third order plate theory and the Reddy layer-wise theory have had a major impact and have led to new research developments and applications. Another profound contribution of Professor Reddy has been in education and knowledge that impact the educational and professional lives of scholarless young people around the world through his textbooks, short courses, and workshops. The highlights of Professor Reddy's contributions that attest for his qualification as an author of research articles that received worldwide recognition as an engineering educator, especially in applied and computational mechanics, are summarized in this contest. Dr. Reddy has a very broad research background that includes applied mathematics and theoretical mechanics, with contributions to the mathematics of finite elements, variational methods and principles in theoretical mechanics, and computational methods with applications to heat transfer, fluid flow, and solid and structural mechanics and coupled phenomena. As a researcher, Dr. Reddy cares about quality than quantity, through the latter exceeds the norm in his field substantially. He has published steadily from the start of his career till now, often in the best journals of his field, spanning about 45 years. For him, writing is an integral part of doing research. He takes pride in seeing his work appear in printing. Dr. Reddy is really someone that impacts with these developments, either at level of engineering education. A close look to the textbooks written by Dr. Reddy show that his teaching philosophy is based on motivate students to fully understand fundamental concepts and mathematical tools necessary to formulate the problems of engineering, and develop creativity and critical thinking in students so as to build solutions to real-life engineering problems. Also, it is very important to identify the professional services that Professor Reddy did. In this respect, we have also to say that Dr. Reddy served as the president of U.S. Association for Computational Mechanics, founding member of the General Council of the International Association of Computational Mechanics, secretary of Fellows of American Academy of Mechanics, member of the Board of Governors of the Society of Engineering Science, chair of the Engineering Mechanics Executive Committee of the American Society of Civil Engineers, among others. This is the great attributions, and this is why Professor Reddy deserves to get this honor and the prize of Leonardo da Vinci. That is someone that is distinguished also the work that in Europe we did and we do in favor of science. Thank you, Professor.
Good morning. So I have very soft voice, so I have to use a microphone. Otherwise, it's very squeaking sound. So my talk would be somewhat different compared to many presentations yesterday. Not that I was able to follow, but I can get the gist of the many of these talks, chemistry and applied physics. So my background actually goes from applied math to engineering science and computational mechanics. So today I will make presentation largely to give some indication of the kind of research I do rather than go into mathematical aspects, because it's highly mathematical. So I'm not here to impress on you that I know mathematics. Hilbert spaces, Sobolev spaces, all these things. So let me start with so this is not just to show that, okay, all right. Does it work? Okay, good, thank you. So the talk, of course, I titled as Computational Mechanics because that's the broad theme of what I'm going to talk about here. So most of you know that when we have to engineer the idea, whether it's a biological, geological, or chemical process, we ultimately have to get some quantitative information. And this quantification of things really come from using tools of mathematics as well as computations. And the phrase computational mechanics has the two words. One is computation, which is obvious that you need to use a numerical method in the computer. But mechanics is a fundamental understanding of any phenomena under the sun, anything. Geological, chemical, biological, anything that you try to probe, understand, and utilize that understanding for the development of new devices or even prosthetics or even diagnostic tools. All of these require an understanding of the physical system and the response of the system under various types of stimuli. That means whether you apply chemical, mechanical, electrical, any kind of stimuli that you use to probe the phenomena. So computational mechanics is a very, very, I think now it stands by itself as a discipline because it is a way to assert the response of any system. And that is where, of course, backgrounds can change. Somebody very good at chemical engineering processes, somebody geological, somebody in mechanical or civil. All of these are possible through the mechanics. Yeah, thank you. So the roadmap is basically I will say a few additional words about computational mechanics. And I consider that to be the third pillar of a stool of investigation. And I will mention those in the coming slides. And then I will talk about some of the research works in a brief way, and then make some closing comments. So let me start with, so one more comment that I like to make, engineering compared to say chemistry or biology, it is not a only beginning, but it tries to find the end to it, meaning solve the problem. Okay, so this is one of the few disciplines along with medicine, a problem-solving discipline. That means the means to get there could be approximated. We do a lot of things, but we want to get to the end of it to try to find the response of the system so that we can design systems for the benefit of mankind, whatever that benefit is. So in that process, we do three things. One, we develop mathematical model. So, okay. So, yeah, good. Thank you. Appreciate it. So I'm basically making a comment here that they are based on physical principles and observations and certain rules of the profession. So for example, anything, constructing a building, it has to pass certain codes as envisioned by the professional society as well as the society at large, right? You cannot just build only using the engineering principles. So all of these are required by the not only society but professional organizations as well as scientific endeavors. So the third thing that I want to mention, this is where I said there are three legs of a stool. That is, first is the developing mathematical model of, this is what I call theoretical formulation. Okay, so listening to all the talks yesterday, there is always a basis, theoretical basis, whether two chemicals adding, producing a third chemical. So that's a formula. Similarly, there are many things in other fields of engineering where you actually have to have these mathematical models. And these are largely founded by laws of physics, like conservation of mass, momenta, energy. These are the fundamental laws of physics that we use. The second is observations and conduct physical experiments. So without which we cannot really determine the characteristics of a system. This is what we call characterization of materials. So, and then third is actually solving what you get from the first two. Because the end result of the first two is a set of equations. And most of the time they are differential equations, nonlinear and coupled. So there is no way you can use the classical methods of analysis to solve them. So you have to use the numerical method. There is no other way. So this is where computational mechanics comes in. And it is a very, very powerful tool because it allows you to, as I will explain in the next slide, these three form the pillars of the scientific study. And of course, some of us are very good at the first ones, some of us very good in the second one, some of us good at the third one. Not everybody does all of them, with intensity, but there is always a strength or depth in one of these three. Of course, it is good to have all three, little bit of it, so that you do a good job of it. But typically, most of us are very good at one of the three. All right, so I want to make a comment here about the computational mechanics. So I'm not overstating. As you will see, most of the governments of most states in the world have made a concerted effort not to do too much testing, especially when it comes to defense, testing the weapons. So what we can do is only simulate the phenomena through computational mechanics to find the residual life of these components. And also, testing is very, very costly and time-consuming. So once you have confidence in your computational technique, then you do most of it by computation. And take, say, for example, whether the Airbus 380 or Boeing 787, they are completely designed by numerical techniques because there was a lot of data from the previous models. So they didn't have to do too much testing of them, physical testing. So we can use numerical techniques because they're only altering either materials or small configuration changes, and all of those can be done. So realistic modeling of physical phenomena through the development of both mathematical models and computational techniques is possible. And numerical simulations allow, see, this is where almost like playing. You can say what if scenarios can be tested. What happens if I change a small part of it in the interest of either saving the material so that cost would be less, or improving the maneuverability or functionality. So all of these can test it in a numerical setting without actually making it in physical testing, because that would be very expensive. So of course you have to always have validation of what you do numerically, but only after that you can talk about all these. So it is really key to many developments. It has been proven, not just I'm saying it, in transportation, communication, design and manufacturing, and fundamental research. And this is very important. Throughout the world, computational mechanics is used, computer tools are used by even experimentalists to make sure that their experiments are set up correctly, especially when you study extreme scales, very, very nano, micro to nano level, or large structures like ships, where the structures are really very, very small in terms of architecture to very large in terms of the entire ship. So that is where computational mechanics can help you, because you cannot solve it by just hand calculations. It has to be computer generated. All right, so the other thing is computational mechanics is used every day by industries, every day. In fact, large percentage of industry only makes use of computational mechanics, less testing. Okay, of course there is always a validation type testing and final certification testing. Whether it's an automobile or aircraft, all components go through certification, and that is where the physical testing comes. But before that, a lot of computational tools are used to design and build them. So it is really, most of the industries use existing commercial finite element codes And I think some of you may have heard Abacus, ANSYS, COMSOL, and so on. These are the, CATIA, automobile industry uses very much. So those are the ones they always just modify. What if I change some part of this structure? How does it help in terms of cost cutting as well as functionality? And so the second thing is, if there is a finite element code or computer program, these are all built on the theories that are available until that date. But any advances made in theory has to be translated again into the modifications of existing computer codes. So that is another area, and I will give an example through my own work. And lastly, we actually can change the paradigm. That means even computational methods can be improved. You cannot just keep using the same, like many of you may be familiar with finite difference technique, which is one of the oldest in the engineering and mathematics area. But now we have very powerful tools in the form of finite elements, finite volume, and then there are other numerical techniques you will see with the interest to solve the physics. It's not like selling a method over the other, but what is the best suited for a given situation. So with those three things, I will start with talking about, for example, studying biological systems. So by the way, I'm just spicing few of the things. I've done a lot of things over the years, but I just want to bring to your attention a couple of different variety of phenomena. So we understand the biological cells are very complicated things in terms of their behavior. We are talking about live cells, okay, not the dead cells. And they can actually multiply, they can even split, degenerate into multiple cells if you really provide enough food for the cell to grow, right? So, but understanding their behavior, especially the mechanical behavior, is not easy. But imagine testing a soft tissue. You have to train it first because it has a lot of different chemicals. And when you do so-called tensile or compression, these kinds of testing, you have to be very, very careful. It's not like a solid body of iron or steel, right? So to understand it, it's a very complex system. So as I sketched here, it has a cell membrane, which is like a bag, and the cell is a large part of it is a fluid, okay? And then it has suspensions like organelles, cytoplasm, and actin filaments, which give the strength and stiffness to the structure. Then there is a nucleus, which is the brain center of the cell. So how does it behave under the action of the external stimuli? So if you do atomic microscope testing, suppose you try to push. So unlike mechanical devices, it has a life. So it senses. It tries to react to the external stimuli, just like a human being. Somebody comes and pushes you, okay? I mean, if it is done suddenly, you may fall because you are not prepared. But if you do slowly, or if you look at the person with the angry face coming towards you, you already try to defend yourself against this, right? So the cell is also same way. So what happened, why I got into this is, there was a published information by different experimentalists and producing for the same cell different results. So I got very curious, how is that possible? Okay, so then we started looking at it, and I won't go into the complete detail of it, as I said few lines in the, but when you model it, you have to take care of all of the ingredients of the cell, okay? And you have to use the, what you call appropriate mathematical model, means how do you actually think the material is behaving? Linearly elastic or viscoelastic? So you have to make those assumptions. And if the one doesn't work compared to experiments, then you have to try another one, okay? So this is where we developed a mathematical model, and then we tested it. So you can see the finite element mesh, the one that is shown on the left, I don't think my pointer works. So the green part is the starting of the cell is configured as a axisymmetric, and then you use the indentation. So you can see the spherical indenter on the top, and when you push it, of course, it's the exaggerated picture of the deformed cell. And then we try to back out the what you call force displacement response. So I'll show you that on the next slide. So you can see there are 3 different color symbols and 1 solid line. The solid line is numerical, and the 3 different experimental results. The solid line can be made to match any of these 3 by merely changing the stiffness of the actin fibers. Okay, so just I want you to understand, actin fibers are generated by the cell. This is the most important part of a cell. When you try to push it, it generates the additional actin fibers to create stiffness. So when the people tested, these 3 people, the rate at which they were loading, if they were loading very quickly, it doesn't have a chance to generate the filaments. So it will be much softer. So we showed through our model that if I change the content, percentage of the actin fibers, I can match any of these 3, which is telling you the rate at which you load the stimuli. That will dictate the response. So this is the kind of finding we can easily do by mathematical modeling. Okay, and so it will help the people who do the testing. Oh, it looks like there is a rate dependency here. And so I will just close that and talk about another topic, shells. And everything around us in nature is a structure that has a thin body and some curvature. I mean, think of your head, your lungs, eardrum, everything in our body is one way or the other is a shell structure. So I'm just showing man-made shells. Okay, you can see them. And then nature. And then you see the heart. The many parts of it is like shell-like. That means thickness of the wall is small compared to the surface area. And they have the ability to take internal pressure and external loads and distribute them as needed into membrane, in addition to transfers. So that is why they call shells or king of structures. Okay, because they are the most efficient there are, and everything. Even if you look at the leaves of a tree, they have curvature. They're not flat, because they are supposed to take loads and distribute it in an efficient way. So, and I'm showing a artery, formation of plaque, and it will grow, right? So we can study all of these phenomena through proper mathematical modeling and study how the plaque buildup takes place and how the stress, the mechanical stress generates because of chemical interaction. Of course, you have to bring the chemistry into it and see how the pressure is going to make a fracture in the cell, the domain, meaning the actual, membrane. And then that is where the atherosclerosis, that is a disease that people experience because of plaque formation in the arteries. So we can study all of these through so-called shell modeling. Okay, so you can see even other kinds of objects, biological and mechanical. Okay, so what are we doing? And the existing models in the commercial codes, they have limitations. So one of the limitations, as you can imagine, you really don't have to have very strong background in shells, but just think of a common sense. I'll give you a balloon. When you start with a balloon, it's a very small rubber band, right? Then you start blowing the pressure. Then what is happening? It is going to blow. After a while, you see, instead of dark blue, suppose the balloon was a blue balloon, it starts becoming a little bit fair color, light blue, because the thickness of the balloon is getting thinner in order to accommodate the large area, right? So that is what happens to the structures. So if you subject them to very large loads, the material has to flow from the thickness into the in-surface. And this is not accounted in the existing models. And that is where we made a change and developed a finite element model so that you can study a variety of structures that I showed you on the previous slide. Okay? And these are my 3 students. I call them lords of shells. Okay, I mean, it's, so, and, you know, Miguel is the rightmost. He is a faculty member now in Mexico. And the middle one is Greg Payet, works for ExxonMobil. And also Roman Arciniega is a faculty member in Peru, Lima, Peru. So all of these worked at one time or the other, all 3 obtained PhD. So this is one of the few equations I have in my slides. But anyway, I've put it there not so much that you need to read and understand, but we bring mathematical model change. So I mentioned that you have to improve the mathematical model of the physics. So just, you cannot get the new information unless you modify your representation of the physics. And that is where we brought the thickness change. And then followed by, all the finite element model development, which is quite a bit of work behind the scenes. This is where I like you to show. So this is a shell structure. You can think of that as a fuselage of an aircraft, okay, subject to, say, any kind of, load. So you can see how efficiently you can model the large deformation of that cell. Not that it will undergo that much, but it is capable. So such a robust element that we developed, it can actually, under the action of any kind of impact load. So how geometrically it is able to deform, and we can predict all of that with certainty. In the next one, so I want to show you this internally pressurized cylinder, all right, whether it's the artery or anything. And if you really, again, this is, I want you to run the animation. So this shell is subjected to internal pressure. We hold the ends. So you can see how it is becoming a larger diameter shell, but the material has to flow from the thickness, because otherwise how can it become a larger diameter shell? So that means thickness change is taking place. And if you see the next slide, and of course all this color coding used to show the state of stress, and all right, so this is the change of thickness as you go from the ends to the inside. And you can see it is as much as 15% change. So it's not small. So it's a very significant effect, and this kind of thing is not in the commercial codes. So we want to help them improve the commercial codes so that people can actually use this for large deformation problems. And another important thing is to show that the thickness stretch is a very important thing, because if you try to predict the state of stress, by the way, many of you probably know or don't know, but stress is a very significant quantity in design of structures. Because just like human being, we all buckle under stress. Okay, that is a chemical stress. Same way materials have this mechanical limitation. If the stress values increase beyond certain allowable, they actually start damaging and they cannot take the load anymore. So we have to predict the stress with a good accuracy. And that is the context in which I'm showing how the standard computer programs like ANSYS and Abacus. So there are 2 kinds of elements. One is based on shells, other is 3-dimensional bodies. And 3-dimensional body is the most general. Okay? So, but we showed through our shell theory that we can predict the 3-dimensional model response. So that is the contribution, because no other way you can predict the correct response. The top curve shows, sorry, I'm not able to show that through arrow here, but you can see the top rectangles. Those are the erroneous response that the shell elements from the commercial codes give. Whereas the red dots are the 3D finite elements, which is the more accurate, and our shell results are matching with that. So that is really very remarkable thing. All right, so but then you say, oh, why don't you use just a three-dimensional elements? And this chart is to show the order of magnitude computational effort. So our shell takes only 66 CPU seconds, whereas two different programs, one takes 2 orders of magnitude, 6488, another code takes 720. So you can see computationally very efficient, yet it gives a three-dimensional state of stress. All right, so the last topic is, well, connected. It's all, one of the things that we are doing now is the non-locality. So again, this phrase non-local means which is not local. So I want to explain a little bit only in terms of the idea. So when you think of a material getting so-called damage, changing something that it cannot actually have the same amount of density or stiffness in the form of modulus of elasticity, it is because the material is getting damaged. So interatomic forces are causing some damage between the material particles. So the way in current state of art is they think the one point is causing this, but that's not correct. Because a collection of points getting damaged weakens the material so that the crack can actually propagate. So this non-local idea is very important, and I'm showing a mega structure like a 14 or 15-story cruise ship, for example. It is made of a lot of things because it want to have sound insulation in addition to the strength and stiffness. And when you think of the environment in which it travels, including the wave motion and cold and hot weather, all of these. So we have to account for all of these in modeling a structure of that size. And it is not, even today's computers cannot handle trillions of degrees of freedom. So we have to find a way to model it. And that is where we like to bring the mathematical models to, I'm showing kind of a global, response. In fact, there are accidents where ships are broken into half, okay? So studying these things is very important. And actually most of the developments in engineering are driven by material science now, designing materials. But who authenticates or evaluates them are the mechanics people, because they are trying to understand the material behavior in the context of their use. And that is where mechanics and computations play a significant role. So anyway, in the interest of time, I will just talk about, one of the method we developed is very low dimensional in terms of the computational effort, yet it predicts the response of a three-dimensional result. Okay, sorry, I jumped one here, yeah. You can see this is the exaggerated deflection curve. In the center, you can see the blue and red. The red is coming from our modified new mathematical model, and the blue is from the 3D finite elements. That is the kind of a reference. And whereas the classical results are showing 25 to 30% of error. So this is significant in the maximum location of the. So the next is about fracture. And fracture is very important in designing any kind of structure that we use, whether it's a medical prosthetic to any of the communication transportation vehicles we use. So why do we have to study? Well, because damage evolves from very, very nano level to micro to macro. So understanding that is a very, very important thing. So again, I have colleagues who work with me in this area. And so you can see that the glass is made in different ways. Okay, I think all of you probably know it. Plate glass, when it breaks into big pieces. If it's a tempered glass, then it breaks into small pieces. So for example, your windshield. So when something happens, either it develops a crack, but if it has to break, it will break into small pieces. Okay? So studying this kind of fracture requires a greater deal of understanding of the material behavior, translating that understanding into mathematical models, and translating mathematical models into computations. And that's exactly what we do. And so again, in the interest of time, our interest is to study all kinds of materials, not just one kind of glass, but any kind of glass, and bring the mechanisms that are present in different kind of material into the mathematical model. So we are working on developing a very deterministic mathematical model development, and bring the probability into the mathematics. That means probability of developing damage, because it cannot be very deterministic, because any minute material defects can cause a different pattern, right? So it is, for a design point of view, you only want to know the ballpark. What is the so-called bounds in which it is going to develop damage, fracture. So I will just say a few words and then go on to, I think this would be very easy to, you can see, you can see the math. So on the left you see the physical testing, on the right is the mathematical model of the same. So although they are not to the scale, but you can see the variation in terms of the crack growth is very close to what you see physically on the left side. On the right side is the computation. And another one is, here is a concrete block. At the bottom it is fixed, and then it is you're pushing. This is like any kind of culvert or any physical structure in man-made buildings. So you can see how the crack initiates at the corner and develops. And we actually can show that even when it goes all the way, how it becomes two pieces. So the method is very robust. All right, so I want to close. And I know that I'm going a little bit here. So the most important message I want to give is, we are really, with these computational tools, we are on the verge of really enormous expansion in our ability to model, represent the physics, and determine the response. This is the most important thing that the computational mechanics brings to the table. So mathematical modeling and numerical simulations together. And of course, a companion experiments of few benchmark problems, because you cannot afford to test everything. And in fact, sometimes you don't know what to test. So this is where computational mechanics brings a valuable insight and a tool to make an impact. And as I said, it is for achieving the technological progress and also to be impactful societally. Thank you for listening to me. And I want to thank especially the people on the both Professor Rodrigo Martins and Alan Tessot, and also Professor Alberto Carpentieri, who is the section chair of engineering. Is not here, but I like to thank him for kind enough to support my nomination, whoever nominated, but in giving me this award. Thank you again.
Thank you so much, Professor Reddy, for this enlightening talk, giving with some example how numerization and simulation are important for many aspects of our everyday life,
Yes,
so thank you very much. So are there some questions, one or two in the audience? Yes, please.
Yeah.
Thank you very much for the enlightening talk. As you may know, in aortic aneurysms, the thickness of the aorta diminishes. And now, since you have a model to account for that, I think it will be a very interesting investigation to see how your model applies to aortic aneurysm. How you think about it?
Yeah, even though I discussed in a broader sense of this thickness change, but it, when you think of artery, same thing. When internal pressure because of blood flow, and when plaque formation takes place, the pressure is going to increase because the amount of area to flow is restricted now. So it will try to elongate. And that is when the thickness of the artery becomes less and leads to a puncturing. Actually can create a what you call crack. And that leads to, of course, heart attacks and other things. Yeah.
Is there another question in the audience?
Yes.
Please.
One of the fathers of applied mathematics, like Jacques-Louis Lyons, mentioned another element which can be considered also as a pillar, and it is the control theory. Because when you want to act on a material, you must optimize and minimize with some cost. My question is, your computational methods can be applied also when there is a control in the problem?
Yes, okay, so it's very important to kind of revisit with you anything that we try to understand. Understanding means try to model it. That is where the physics comes in, okay? That means whatever laws govern. In chemistry, these are chemistry equations. In biology, we do not have the laws yet. So only observations, clinical tests. And then you imagine by looking at what is happening, there is a transport of species, and you create a mathematical model of it. So you understand the ability to understand and translate that understanding into mathematical model, then to computational model. So you can see they both depend upon your understanding of the physics. That is the most important thing. So it cannot be just number crunching. It has to be physics-based modeling. So when we talk about material properties, it's actually misnomer because it is a structural property. Okay, see that is where metamaterials are coming. We are designing material now. It is the property of the structure, not of a point. Okay, so yes, we can model provided we understand it well. So.
Okay, so please join me to thank again Professor Reddy and congratulate him for this very well-deserved Leonardo da Vinci Award. So, congratulations.
Can you announce the Blaise Pascal start now? Okay, so now we will start distinguish our awardees with the Blaise Pascal medal, and this is something to honor excellent works and scientific work done by fellows or people that will turn fellows of our academy due to the distinguished activities that they did in the different fields. And we will ask the head of engineering division to present the first award, please.
And the medal after?
After him, we will go down with him.
Good evening. My name is George Voyages, and I would like to begin by thanking.
Dear ladies and gentlemen, dear colleagues, it is my greatest pleasure to introduce Professor George Voyages, who is the winner of the Pascal Medal 2023. in engineering. He is an outstanding worldwide scientist in plasticity and damage modeling of material behavior, including the bridging of length scales. He presently is the chair professor at the Department of Civil and Environmental Engineering of Louisiana State University. He is also the director of Center of Geoinformatics at the same university. Professor Voyages is foreign member of different scientific academies in Europe and in Asia, and was the recipient of several prestigious awards, such as Nadai Medal from the American Society of Mechanical Engineers, Doctorate Honoris Causa from Poznań University of Technology in Poland, Distinguished Member of the American Society of Civil Engineers, Cannes International Medal for Outstanding Lifelong Contribution to the Field of Plasticity, Nathan Newmark Medal from ACCE. He was also the most cited author between 2005 and 2008 of the International Journal of Solid and Structures. Professor Voyages is also very active in professional scientific societies. He is a member of the board of directors of the International Conference of Damage Mechanics, fellow of the American Institute of Aeronautics and Astronautics, fellow of the American Society of Engineering Education, chair of the executive committee in the ASME Material Division, president of the Society of Engineering Science, member of the editorial advisory board for the International Journals Plasticity and Engineering Mechanics, chief of the founding editor of the Journal of Nanomechanics and Micromechanics. Professor Voyages is author or co-author of a large number of scientific papers published in peer-reviewed international journals. He has 69 H-index with more than 16,000 citations on Scholar Google, and he has an H-index of 58 in Scopus with more than 12,000 citations. He authored 11 seminal books and edited 13 books by the major international publishers. He presented invited keynotes and plenary lectures at over 430 meetings and conferences. He also acted as the supervisor over 40 visiting scientists and postdoctoral associates, as well as 39 PhD students. For all the above reported reasons, and based on the positive judgment of the scientific committee of the engineering division, I am sincerely convinced that Professor Voyages is fully deserving for the EurASc Pascal Medal 2023 in engineering. Thank you. Professor Voyages is not here. Therefore, he cannot live here by Zoom, but he gave us a thank you video that we can see, and then we can attend his presentation that is registered. Okay? I think that the video can. Yes. Thank you.
Good evening. My name is George Voyages, and I would like to begin by thanking the European Academy of Sciences for giving me the prestigious Blaise Pascal Medal. This recognition goes way beyond anything I ever imagined as a doctoral student at Columbia University in New York City. Working with my students has been the catalyst of my success in my academic year. The importance of this interaction is to challenge them, but also allow them to interact with you through the evolution of their research work. Do not be afraid of failure, as it is the gate of knowledge, and eventual success in your endeavors. Always be proactive in starting new areas and concepts, as this may lead to proposing groundbreaking solutions for real-life problems. I would like to thank my family for their support over all these years. The singular person most responsible is my lovely wife, Christina. She has supported me through the moves, the job changes, long hours, and challenging projects. My experience in industry and my academic appointment overseas has allowed me to think in a more global sense and at the same time stay relevant to engineering applications in my research endeavors. That's what keeps me grounded and gives me the ability to continue to do all this work. It is a privilege being an engineer. Thank you again for this great recognition.
That is titled A Physics-Based Crystal Plasticity Model with Applications in Simulation of Micropillar Compression and Strengthening Effect of Multilayered Copper Graphene Nanocomposites. Okay, please see the presentation.
I am George Z. Voyages, and I'm in the Department of Civil and Environmental Engineering at Louisiana State University in Baton Rouge, Louisiana, in USA. The topic of my presentation is a physics-based crystal plasticity model with applications in simulation of micropillar compression and strengthening effect of multi-layered copper graphene nanocomposites. The outline of my talk, I'll start with motivation and objectives, followed by slip systems for FCC crystal from experiments, specimen preparation and loading, computation of GND densities, kinematic and crystal plasticity formulation, numerical setup for crystal plasticity finite element implementation, simulation of micropillar compression, strengthening effect of multi-layered copper graphene nanocomposites. Motivation and objectives. Micropillar compression test gives important information on the mechanical behavior of low volume materials and the relationship between dislocation, patterning, deformation modes, and strengthening mechanisms in metals. The goal of this study is to describe the microstructural evolution of dislocation densities in the materials during plastic deformation. To do this, crystal plasticity model accommodates various dislocation mechanisms. In this study, we address the evolution of geometrically necessary dislocations and statistically stored dislocations in face center cubic single crystal copper via a micropillar compression test. Slip systems for FCC crystal and experiments. The copper single crystalline specimens are prepared for micropillar compression. The figure is the description of typical FCC slip systems and Schmidt factors for uniaxial stress state in the y-axis. Using the Schmidt-Boas notation, A, B, C, D denote the slip planes and numbers for the slip directions 1 through 6. Considering the Schmidt factors for slip systems, B2, B4, C1, C3 play the primary role for the 110 crystal orientation. Specimen preparation and loading. The in situ experimental procedure for the micropillar compression test is as follows. The square shape of micropillars is created by a focused ion beam as shown in the SEM image. The compression tests were conducted using an in situ nano indentation platform. EBSD diffraction EBSD diffraction patterns were recorded during the mechanical test to achieve mapping of the GND population. To estimate the GND densities, experimentally, the elastic distortion is captured by the high angular resolution electron backscatter diffraction technique and it can be solved by the inversion method. In the simulation, the Nye-Kroner-Bilby dislocation tensor is expressed as follows. In terms of the plastic deformation gradient tensor, and the G&D densities can be obtained by solving the system of equations. Now let us discuss the framework of crystal plasticity. The total deformation gradient can be decomposed into elastic and plastic components. The lattice vectors will be used to compute the texture development of the crystal structure. The plastic flow rate is associated with the superposition of the slip rates, as is shown here. The flow rule is based on the OR1 equation. The flow rule describes the kinetics of the dislocation population, such as the thermal activation mechanism and drag mechanism. The critical resolved stresses are the function of GNDs and SSDs. Now we have the numerical setup for the crystal plasticity finite element implementation. The figure shows the initial configuration of the micropillar sample. In this configuration, we try to apply the real-life condition of the experimental setup sample, such as geometrical imperfections, misalignments, as you can see here, and eccentric location of the nano indentation as shown in the SEM image. And this is depicted in the SEM as you see here. Localized debris. Now, the numerical setup for the crystal plasticity finite element implementation for Model 2, which is the ideal case. In this configuration, we consider the ideal conditions of the experimental sample without any geometrical imperfections, misalignments, and eccentric location of the nano indenter. To validate the model, we try to compare the deformation measurements between experiments and simulations. The top row shows the experiment from 0% strain all the way to 9.3% strain. The associated simulations results are described in the bottom row, as you can see here. Considering the geometrical imperfections in the micropillar sample, the deformed configuration of the simulations are well matched with the corresponding experiments in terms of the trace of plastic deformation and apparent slip bands. So you see here the slip bands, which are from the simulation, which are mimicking the experimental values that you can see here. Now, figure A illustrates the variation of stress strain curves for the 10 micrometer sample sizes. It is important to note that the degree of the initial dislocation densities in the material will affect the material hardening and the value of the yield stress of each material. The stress strain curve from the simulation closely matched the experimental results shown in figure B. The stress strain curve for Model 1 follows experiment number 2, as you can see here. And that of Model 5 follows experiment number 5. The evolution of the total G&D density captured by high resolution EBSD is presented in the top row. Experimental results. The simulation results are also compared with the corresponding experiments in the bottom row that you can see here. So this is for Model 1, and this is for Model 2, the perfect simulation, and this is Model 1, which depicts the more real, factual, simulation. For the initial state, it is noted that the penetration of the tiny particle on the top corner that you see here produces a high accumulation of total GND density. Bending mode is observed at 2%. Compressive strain due to the misalignment of the indenture. At 5.7% compressive strain, the additional slip bands are initiated with more accumulation of GND. Finally, a considerable GND population is observed through the slip bands at 9.3 compressive strain, and this is depicted in the simulation, in the factual, in the accurate simulation. Now, numerical results, total GNDs. Model 1 accurately predicts the propagation of shear localization from the top right corner of the micropillar corresponding to the three-dimensional contour mappings. On the other hand, there is no bending mode in Model 2, resulting in the barrel shape of the final configuration. Instead, the high accumulation of GND densities is expected in the primary active slip system in Model 2. 3 cross-sections were selected to determine if the distribution of the total GND densities along the outer surface shows an identical trend internally. Section 1 in figure A1 shows a similar distribution of the outer surface of the specimen in the XY plane at the 9.3 strain gauge. This is because the specimen is subjected to the influence of particle and boundary conditions. In section 2, since the indenter's misalignment also causes bending in the YZ plane, a high GNT is formed through the Z direction on the top surface, and the influence of the boundary conditions around the left bottom region is hardly seen. Section 3 shows GND mappings different from the GND distributions shown in the previous sections 1 and 2. Crossing GND distribution was shown at both the top left and right corners due to the influence of bending. Figure A1, as you can see here, for Model 1 shows the distribution of high GNDs, which is considerably influenced by boundary conditions. High GND accumulation was achieved due to the boundary conditions at the bottom caused by milling during the manufacturing process. Comparing the total SSD with the total immobile SSD density, the total mobile dislocation density is distributed inside based on the boundary of the total immobile SSD density. The propagation of the mobile dislocation densities is significantly reduced due to the force dislocation densities in terms of the accumulation of GND. And immobile densities as shown in figure C. The occurrence of the most plastic deformation corresponds to the high distribution of total immobile dislocation density. To determine the internal distribution of dislocation densities, the slip system of each dislocation density were classified into 4 groups. The figures for the Model 1 describe the probability of GNDs, mobile SSDs, and immobile SSDs based on the 4 groups that you see here. The distribution of GNDs is the top row, and they are unaffected by the active and inactive slip systems, exhibiting an even distribution across all classifications. Immobile SSDs, on the other hand, are primarily stored in inactive slip systems A2, A3, D1, D4, which share the identical Burgers vectors of the active slip systems. Mobile SSDs are largely located in the active slip system, as shown in the bottom row of the figure. The micropillar is discretized with 3 different mesh densities with the identical element type used in all of them. In the simulation of micropillar compression for Model 2, the total number of elements is 12,096 for the coarse mesh density, with the mesh size of 0.8 micrometer. Now, for the second case of with DH of 0.5 micrometer, we have 36,580 elements. That is the middle mesh that you see right here. And finally, for the fine mesh of DH.3 micrometer, we use 176,305 elements. The figures provide the 3-dimensional contour mappings of the total accumulated plastic slip with different mesh sizes at 9.3 compressive strain. The spatial distributions of total accumulated slip for all cases exhibit an equivalent degree of values along with the slip bands at the top and bottom regions of the micropillar, compression. Considering the degree of difference in 3 different cases, the simulation results demonstrate the independence of the mesh density. Lastly, we'll show the probabilities of the accumulated dislocations in the micropillar sample. The total mobile SSD density is depicted in yellow. The total immobile SSD in blue. And the total GND density in pink colors, respectively. The average values of each distribution at 9.3 strain are very close to the experimental observations in terms of the amount of accumulated dislocation populations. The mean value of immobile SSD is bigger than mobile SSD density by about 100 times, and total GND density is distinguished by about 10 times bigger than immobile SSD density. The next example we're using is the strengthening effect of multi-layered copper graphene nanocomposites. So in this case, we're using crystal plasticity finite element simulations, both internal and external dislocation sources, and account for the dislocation microstructure in an average sense. The numerical results are compared with the existing experiments that you will see in a minute with in situ TEM to discover differences in dislocation structures. The observation suggests that dislocation mechanisms such as surface nucleation or single arm model be responsible for the size effect observed in small scale specimens. Now, here we show the manufacturing process of the copper graphene composites. The slide describes the manufacturing process. A single graphene layer is deposited in the copper foil. Graphene layer in the copper foil using thermal chemical vapor deposition. TEM images indicate the different layers of composites, such as one layer of graphene sandwiched by 2 copper layers on the top left corner. And, as we proceed, you see how we manufacture the copper graphene. And Two different kinds of configurations are considered in the numerical setup of the crystal plasticity finite element calculations to compare with corresponding experiments on copper graphene. One is the copper graphene composite and the other is copper polycrystal. So you have here copper graphene composite, copper graphene composite, copper graphene composite, and simply a copper polycrystal without any graphene. The thickness of the graphene layer is approximately 0.3 nanometers, so it is modeled as a membrane element. Each copper layer has its local crystallographic orientation. The rigid body constraint and displacement controlled loading are applied to the nano indenter. The loading strain rate is 0.002 per second. The stress strain curves on the left-hand side are obtained from the experiments with 3 copper graphene composites and 1 copper polycrystal. So you see here we have the 3 copper graphene and 1 copper polycrystal. The numerical results showed a trend in strengthening effect on reducing the metal repeated layer spacing and decreasing the number of graphene layers, as you can see here. The top left in this case corresponds to copper polycrystal, and the others are copper graphene composite systems. Copper graphene, copper graphene, copper graphene. The range of total dislocation density is from 10 to 14 to 10 to 15. The accumulation of total dislocations for the polycrystal and for the copper graphene 200 are comparable as shown in figures A and B. The accumulation of total dislocations, which are depicted in black dashed lines. In contrast with the copper 100, the high accumulation of total dislocation density in the samples for couple graphene 125 and couple graphene 070 shows the hole patch-like effect as a result of the number of graphene layers. The evolution of probability distribution of total dislocation density follows the color sequence of blue, orange, yellow, and green. Simulations for copper graphene composites show more widely distributed probability in the 3D mappings than those of copper 100. In the meantime, copper graphene composite systems demonstrate a hole patch-like strengthening effect because the combination of single arm source and surface nucleation mechanisms surpasses the balance between generation and depletion of dislocations in the samples. The experiments on the left side show the concentration of high dislocation density on the top copper layer. This is because the shape of the top layer, which is fabricated with some curvature, induces a high degree of slip localization. The deformed configurations of the simulations show strong slim bands and traces of the plastic deformation on the top layer of copper graphene composites, which are matched with the distribution of dislocation density and deformation measurements in the TEM images, and you can see them here. More specifically, the slip bands and complex distribution of dislocations are formed in the upper layer of copper as shown in these figures. The 3D contour mappings indicate the total dislocation density with an increase in compressive strain. As shown in the TEM image A4, in the deformed configuration of the sample, a high accumulation of dislocation density is identified above the graphene layer. The simulation results well matched the distribution of the dislocation density. As the layer spacing is reduced, the chance of depletion of dislocations through free surfaces is reduced. In this simulation, total immobile SSD density is a major strain hardening contribution. The total GND density does not significant impact on the strengthening effect on the copper graphene composites due to the lack of strain gradient on the sample. Statistical analysis shows the direct correlation with a hole patch-like effect resulting from increased graphene layers. In conclusion, the new physics-based crystal plasticity model is validated with experiments of micropillar compression. Also, it shows the strengthening effect of multi-layered copper graphene nanocomposites. This work gives an insight into the microstructural evolution of dislocation populations during the plastic deformation of the metals. Thank you for your attention. And here are some references of the work presented here. And we just published a second paper, which is based on the copper graphene in the same journal, Journal of Mechanics and Physics of Solids, which hopefully will appear in early 2024.
We will go for the next presenter. That will be the Blaise Pascal Medal in the field of mathematics, and will be Professor Science to make.
Dear President and Vice President, dear colleagues, it's for me a big pleasure and also an honor to introduce Professor Athanasios Fokas, who is the winner of the medal this year. Professor Fokas was born in the island of Kefalonia in western Greece, and he has a remarkable range of titles in education, because he first got a degree in aeronautics from Imperial College in 1975. Then he went on to Caltech, where he got a PhD in applied mathematics in 1979. And finally, in 1986, he got a degree in medicine. So he's in aeronautics, mathematics, and medicine. He's been employed at various prestigious institutions. For instance, he very early in his life, he became a full professor at Clarkson University. Then in 1996, he was appointed to a chair in applied mathematics at Imperial College. And since the year 2002, he holds a chair in nonlinear mathematical science in Cambridge. He's got many prizes. I will only be citing here a few. See, he's got a very prestigious Naylor Prize from the London Mathematical Society. He also has the most important prize that is awarded by the Academy of Athens. The same year, 2004, that he got his prize from the Academy of Science, he was inducted into the Academy. This is a remarkable thing, because this academy is very, very small in terms of number of academicians. So in fact, he's only the sixth mathematician that has been appointed an academician there. And he also has the Order of Phoenix from his natal country, from Greece. He has several honorary degrees, and he's also been head of, or president maybe, of the Board of Trustees of the National library in Athens, in Greece. His mathematical interests are very wide. I think first and foremost, maybe in terms of contributions, is the solution of boundary value problems for partial differential equations. You know, even if you are not a mathematician, those are very important. In fact, the two previous presentations that we heard in the morning, even though the authors were kind enough not to show the partial differential equations or the boundary conditions, they were boundary value problems for partial differential equations. And even maybe those of you who are not the mathematicians but have had some training as undergraduates in partial differential equations, you know that the easiest available methods to solve them, unfortunately, they will not always work, are based on series expansion, maybe Fourier expansions and other expansions, and in the parallel thing of transforms, maybe the Fourier transform or the Laplace transform that I think many scientists are familiar with. Well, those techniques, as anything else in life, are not without problems, and sometimes they cannot be really used for numerical work because they have problems near the boundary, they don't converge uniformly, and so on. And many of those deficiencies can be sorted out by using the so-called focus transformation. So it's a very important transformation that is named after Professor Focus. He's also worked on medical images and inverse problems, even though I don't think his contributions to those techniques are related to the fact that he's a medical doctor, and he's also contributed to more purer branches of mathematics. One of the main, or maybe the main, unknown in mathematical analysis is this Riemann hypothesis concerning the Riemann function, introduced by Euler and Riemann, and Professor Focus has worked extensively in the asymptotics of these very important functions. And there are many other things like fluid mechanics, complex analysis, protein folding, and very many contributions. And I believe his contributions are not only very numerous and wide within mathematics, but I would say that he's also interested in very many different things. And very recently, he's completed a book on creativity and the way different people understand different things in life. And this book is based on the wide experience he has in many different fields. So he's been able to put together the different ways in which people of different fields understand science. So I think for these reasons, Professor Focus is a very worthy recipient of the medal this year.
Okay, and so I can use this. Mr. President, Mr. Vice President, thank you very much for this great honor. Especially I'd like to thank the Mathematics Section Committee, and especially her head, Professor Sarna. And it is really I'm very honored to be among this distinguished group of recipients, but before I speak, please let me say that it's always kind of embarrassing to be introduced. Often the introduction is inaccurate, and it is such a privilege to have been introduced by you, because your introduction was very meaningful, not in terms of awards, but in terms of what I have tried to achieve. And of course, it means that you have a very deep understanding of some of the things I have done. So I'm deeply grateful for your great introduction. Okay, so this is, of course, a general gathering. Therefore, my talk will not be for specialists. My talk will emphasize ideas and even more philosophy than anything else. So I hope it will be better understood or appreciated, whatever. You see, as it was already mentioned in the introduction, so I use, how do I go this way, probably, yes. Yes, I have recently written this book, Ways of Comprehending, which introduces a novel approach to understanding, stating that this requires a deep analysis of neuronal mechanisms. Obviously, it is impossible to understand how you understand without understanding how the brain works. And in particular, for example, it emphasizes that every conscious experience is preceded by an unconscious process. It also notes that this process of understanding is facilitated by the use of certain basic notions, which are basic because they reflect fundamental neuronal mechanisms. And among these fundamental notions are the notions of associations. For example, we use all the time that we think by analogy, of abstraction, of generalization, and of this fantastically important dialectic pair of unification versus reduction. So examples par excellence of generalization and unification are respectively mathematics and physics. Indeed, mathematics is nothing but generalizing. I never forget, you see, I have the fortune to have worked with some great people in my life. One of them was Israel Moiseyevich Gelfand, and I remember early on in our work, he told me, Thanasis, something is important in mathematics if and only if generalizes. And I always emphasize to students that mathematics is extremely simple. Each step is extremely simple. So you build hierarchically, starting from elementary axioms, you see. What makes mathematics complicated is the ability of the human brain to build these fantastically complicated structures, of course also using the process of abstraction, through this process of building. This means that it is natural for the brain to attempt to reverse this process and reduce something very complicated to its basic, simple ingredients. And occasionally, this occurs asymptotically. Professor Reddy noted this connection, of course, between mathematics and physics through mathematical modeling. So you can see this in physical processes. For example, you see that asymptotically, a water wave of certain type reduces to solitary waves. So these are the basic ingredients, which of course are reflected in the mathematical equations that model this process. So one can say that the mathematical language of asymptotic analysis provides a rigorous way of understanding this process of reduction. And I'm going to spend 5 minutes maybe in my talk exemplifying this through the analysis of the very famous problem that was mentioned earlier of asymptotics of the Riemann function. But regarding unification, I noted earlier that physics provides the example of excellence for unification. But of course, mathematicians are also attempt to achieve unification, and I will begin the technical part of my talk with presenting such a unification, which is called, I called it the unified transform, but many people call it now the focus method or the focus transform, which provides a unification of various types, as it will become clear. You see, it was mentioned already in your talk that we have no choice when the problem is complicated, but to use the computer, you see. But I want, as it will become clear in this first part, this is not only for complicated problems, you see, but also even if, as it was mentioned earlier, you have a very simple linear boundary value problem and you solve it either with, in terms of a transform or a series. Finally, if you want to get an answer, as you said, if you want an engineer and you want to do something practical, you have to compute, you see. I never forget, I was teaching at Caltech as a graduate student, some students asked, and how do we compute? After I presented this course in transforms, and how do we compute this final integral? You see, a very simple question. And I answer at the time in this highly non-pedagogical way. You know, this is a course in analysis, in transforms. If you want to compute, you have to learn finite difference and do it, you know, which is terrible. You see, one of the great advantages of this unified transform, which I will say a couple of words, is that it is ideal for computation, you see, and undergraduates can compute it. So I hope that it will become more prevalent, especially nowadays. It is terrible that everybody uses so much the computer to stop at, okay, so let's say, so the first type of unification is, you see, if you think of transform, of solving linear PDEs, which are, of course, are the most, PDEs, as already mentioned, are so fundamental, I don't have to advertise them, but there were two different approaches used. Maybe the most well-known is the approach via transform or series. You see, alternatively, there was a brilliant mathematician, actually at Cambridge, Green, who introduced this alternative way, but in some sense it's ineffective, because although it gives you an integral representation, it cannot really handle correctly the boundary conditions, so it can be considered that my approach provides a unification of these two different ways. So this is the first way that the word unification comes into mind. You see, these people, de Koning and the others, wrote this about my method, and I was very pleased that the editor of SciAm Reviews wrote an article. I didn't know, and I still don't know the editor, but he wrote that this is a very important development because it's like the Fosbury method in jumping that introduced a completely new way. And this is indeed the case. It's indeed the case. To be honest, for many years, I was worried because I said, I mean, you know, we're talking now, again, Gelfand told me, Thanasis, it's not a problem to compete with your contemporaries, but be very careful when you compete with the classics, you know. So can you do better than Fourier? Can you better than Laplace? I mean, this was the golden era of mathematics, and these were giants, you see. And the answer is, yes, you can. Actually, I'll make, because I'm in a very good mood, since you were so kind to give me this great award, I will make even a statement that Fourier, in some sense, and this maybe should not be quoted, but I think it's true, had a negative impact. In what sense? You see, Fourier solved the famous heat equation through Fourier series. Then Fourier never stopped. Then he understood that there was another tool which he introduced, much more powerful, which was the Fourier transform. However, he never asked the following question. Okay, I have a new tool. Could I use this to use my first problem on the finite interval instead of the Fourier series. Had he done that, I believe that it would have been great for mathematics because nobody would have used Fourier series, which is completely terrible, except if it happened that you have periodic boundary conditions. Okay, so all this I understood through my method. So what is my method? My method, by the way, there is this book which we published last year with the head of the physics department of Harvard University, Efthymios Kaxiras, and there are several chapters in this about this new method, and it's my hope that now it will be used. Already it is used at some universities, but in my opinion, in not many, and hopefully this will allow, because we owe this to the students. I mean, you said earlier in your talk, Professor Eddy, that when you have a new improvement, it has to be coded. You see, now there's a huge improvement. It has to be taught, okay? So what is the idea of the new method? The idea of the new method is that you leave the real line and you go to the complex plane. You see, the complex plane has much more freedom. So let me give you a very quick example. This is the most elementary problem you could ask to solve as a boundary value problem, the heat equation on the half line, and it gives you this final expression. You see this final expression, everything is explicit, as you see, because it's given in terms of initial conditions and boundary conditions. So in principle, but not in practice, you could compute this integral. But note that if you really scrutinize carefully this, immediately you should be worried. Why you should be worried? Because you see this u on the left-hand side is the solution of the problem, which means when x equals 0, this u should go to g naught of t that you gave as boundary condition. But if you naively put in there, inside the solution, x equals 0, because sine of 0 vanishes, you will get 0. Okay? This is what it was mentioned before, that this solution is not uniformly convergent. It means it's a bad solution. It's a bad representation. You see, it is not written in any book on transforms, this obvious fact. And here is my statement. My statement is that this is a generic problem. Has nothing to do with the heat equation on the half line. Any problem you will ever solve with any transform, unless you have boundary conditions, will have this pathology. And because of that, it's not only mathematically suspicious, but you cannot use it, you cannot implement it numerically. So, but of course, there is much more worse problems than that. I mentioned already, Gelfand said, something is important if and only if it generalizes. This is not important. Why is not important? Because suppose I give you a third order PDE, which are very physical, Stokes equation. How do you solve it? What is the transform? It doesn't exist. You see? But my transform it generalizes, so I will not spend time telling you all the limitations of the classical approaches. There is, if you look at the last equation, the Stokes equation, there were at the time at Cambridge two Sir Georges. Sir George Stokes, who did this, and Sir George Airy, that you know from Airy function. And they both, by the way, attempted to resolve, to understand why you have solitons, and they both missed it. But doesn't matter. What is important is that this equation is physical, but transforms, existing transforms before the development of my method, were incapable of doing this. So here is a new transform. As you see, the important is you leave the real line and go to the complex plane. I wrote these two to see the unified essence of this, namely the two formulae, the formula for the second order problem and the third order problem are very similar. I will not give you detail. I will only tell you that in contrast to the previous situation, this is elementary to implement because it lives on a contour where for large k you have exponential decay, and I will only show you one. So this, for example, a typical problem, as you see, the boundary condition is quite complicated, despite the fact here is the numerical implementation of the final formula. So, and as I said, undergraduates can do it. So it is, I believe, unacceptable not to teach the undergraduates this new approach. Now for the next 5, 7, 10 minutes, whatever I have in my talk, I will talk about this idea of the connection between asymptotics and reduction, and this, by the way, is the finite interval. You see, no series, as you see. There's only integrals. So no series. This is the mistake of Fourier. You see, series are terrible for various reasons, you see. And this formula, as you see, is as elegant and as numerically implementable as the previous one. Okay, let's go to Riemann. You see, of course, this is completely new, so it is natural that had numerous implications in many different areas. I do not have time to discuss them, but I don't work in this area anymore, you see, but I'm sure there will be even more developments, you see. So there are many applications. For example, for elliptic problems, you can do it. I only talk about evolution equations, etc. When I was at Caltech, Fromberg was already tenure at Caltech when I was a student, so I was very surprised to see later on that he wrote a paper on my methods. It was very emotional for me, etc. Okay, let's go to Riemann. For a few minutes, let's go to Riemann. 5 minutes, perfect. 5 minutes is enough, you see. So what is the Riemann hypothesis? Euler introduced a function, a sum, which is the Riemann function, but this function was defined only for very specific values of what it depends on, but then the great Riemann understood that you can define this for all values if you analytically continue. It means what? If you go to the complex plane. So if you go to the complex plane, you can define the Riemann function on the complex plane, and in terms of calling x and y, you call it sigma and t, because Riemann introduced this, you see? So what is the Riemann hypothesis? So in principle, we know everything in the complex plane about this function, except in the sum terra incognita, which is a strip from t equals 0 to t infinity, and sigma equals 0 to sigma equals 1. So Riemann hypothesis is in this unknown region, the function never becomes 0, except on the line 1/2, where Hardy from Cambridge proved that indeed there exist infinitely many zeros. Of course, using computer, you can see that there are no zeros up to 10 to the 32, very high value. But still, 1032 is very small compared to, but this shows that really the problem is for large t. Lindelof understood that, so he said, what is the behavior of this function for large t? You see, and he speculated something, and this is called Lindelof's hypothesis. And I started 14 years ago working on these asymptotics, at the beginning secretly at Cambridge, because this is supposed to be a problem in pure mathematics. So I didn't want my colleagues to think that I got crazy, you see. First, we wrote this paper. This paper is a heroic paper. Maybe it's the most heroic paper I have been involved with. Why? Because, as you know, if you know asymptotics, you know when you go to the right, to more orders, situation gets worse. Not with Riemann. The first term is transcendental, but all the others are explicit. And in this paper, following some early work of Riemann and Siegel, we did asymptotics to all orders. But again, because the first order is transcendental, you don't have Lindelof hypothesis. So I will finish by telling you another unification. So for reasons which I cannot explain, I discovered this top equation satisfied by the Riemann function. You see, I communicated this equation to a famous person working in this area, and he told me, Thanasis, it cannot be true. I said, why? I have proven it. He says, because if it is true, we would have known it, since we know everything about Riemann. It turns out that it's both true and it was unknown. So my idea, so the classical approach is to do asymptotics directly on the Riemann function. My idea was to embed the Riemann function in this structure and then do asymptotics of this structure. And I do not have time to do it, to say anything. All I will say is, and I will complete my talk, is that the analysis of this equation is very, very complicated. But we have a result, and this result is based on what? Is based on, again, the complex plane. So for a long time, I was not able to compute effectively this integral defined by I3. As you see, this I3 involves the Riemann function at 1/2, which means in the forbidden domain. The main idea, the main ingredient was that you deform in the complex plane, and if you take this capital Y to be greater than 1/2, it turns out that you escape the forbidden domain, and this allowed us to have a result now which is of the type of Lindelof hypothesis. I will stop here, and I will thank you very much, both for this award and for your patience. Thank you very much.
So thank you so much, Professor Focas, for this almost philosophical talk, and we make us think about all these comprehension roots of these very important questions.
Thank you.
If there is in the audience one question, one or
One.
two, okay, because
Thank you, Professor Focas, and congratulations for this honor. Just one question, and very brief, because there are more people. Maurice Dirac, the Nobel Prize in 1935, I don't remember, together with Schrödinger and together with Heisenberg for the discovery of quantum mechanics. He was a mathematician himself. He was working in Cambridge, and he said that equations should be expressed always with beauty.
Almost?
Always with beauty.
I didn't say.
Okay.
Of course, 100%. 100%.
Beauty.
Of course, you're absolutely right. Absolutely correct. Absolutely correct. Thank you for reminding me, because I want to make the remark that I'm so pleased to receive this award in this beautiful place, because aesthetics has always been crucial in my work. You see, although I am supposed to be an applied mathematician, in some sense, I'm closer to pure mathematicians in the following sense. I have never worked in an area because it was going to be fashionable or gave a lot of grants or whatever. There was only two criteria. One was importance, but this importance could be like Riemann, not necessarily in terms of applications, like medical imaging. And the second, equally important, aesthetics.
so the last question.
Fascinating. I'm a biologist, not a mathematician, but can mathematicians imagine that there could be more than 4 operators in mathematics? I mean, you have plus and minus, division and multiplication. Are those the only 4 operators that mathematicians can use or dream up or be creative about?
No, you see, I'm not, I always know when to say that I don't know, and my answer simply is I don't know. But I could pay you back by saying that I am extremely interested in biology, and with respect to biology, I have worked, and I will finish here, I have worked with 2 people which were both giants with completely different points of view. One was Joe Keller, that anything that could be mathematized, he mathematized it. I wrote with him a paper on modeling of chronic myelogenous leukemia, for example. And the other was Israel Moiseyevich Gelfand, who claimed that mathematics is not the correct language of biology, perhaps consistent with your statement earlier that in biology we don't have the rules. Anyway, thank you very much for your patience.
Okay, thank you.